Okay, this is going to be a short introduction to fields over the course of about 5 videos probably, so not that short, but each video hopefully won't be too long. We'll cover the basics of mapping fields, visualising fields with field lines, looking at the shapes of those fields and the properties that different shaped fields have, then look at the idea of field strength and move on to the potential of a field. There's quite a lot of stuff this, but it will give you a really good grounding in fields. That is gravitational fields, electric fields, any field you like really. It should be useful for that. So we'll start off with mapping fields, mapping out field lines and visualising fields. So a field can be mapped using a small test object that interacts with the field. Now you've probably got experience of this if you have mapped the magnetic field around a bar magnet. You probably used something that interacted with that field, another small magnet, probably a compass needle in a plotting compass. So you've used a small object that interacted with the magnetic field in order to map the field out, and we'll look at that on the next slide just to remind you how that went. What object could we use to map out a gravitational field? What interacts with a gravitational field? Well, we'd have to pick an object that had mass, so you might want to get a weight on a bit of string or something like that. That would interact with a gravitational field. And for an electric field, you want an object that has charge that will interact with that field. Now there's a convention here that the test object has a positive charge, because obviously it could be a positive or negative charge. There is no equivalent of that for gravitational field. There's no negative mass that we know of. So gravitational field is just a small object with a mass, but for an electric field we'd use a small positive test charge. Now, I keep saying the word small. Why is that? Well, the test object must have a small mass or charge or whatever, so that it doesn't affect the other object too much. So if you're trying to map the gravitational field, of the Earth, we would choose a test object that is small in mass terms compared with the Earth. That's quite easy to do. Likewise for your magnetic field, when you did a bar magnet, you used another magnet that was a lot smaller and a lot weaker than the bar magnet in order to plot the field. So we'll keep coming up with this again and again as we go through this. So let's just recap how you would have mapped a field, mapping the magnetic field around a bar magnet. What you probably did was take a plotting compass which had a needle in it and place that at a point on your magnet and plotted the direction of the force acting on the needle, and then you would have moved the plotting compass along, plotted another point, and so on, building up a series of dots which you could then join up to form a field line. Whoops, not too straight. You then probably would have started again in a number of different positions. Whoops, there we go, and done exactly the same thing. And I imagine the following diagram will look familiar to you. Showing the field around a bar magnet. A couple of things to note about this diagram that you may have looked at the time, or you may not have done. I'll just quickly chuck in a few more field lines as well. And that's to do with the spacing of the field lines. So the more closely spaced the field lines are, the stronger the field is in that place. Now you can see that the field lines here near a pole of the magnet are much more closely spaced than they are here, far away from the pole, or even here near the middle of the magnet. So where field lines are close together, the field is strong. Where they're further apart, the field is weaker. And that applies for all fields. So that's how you'd plot out a magnetic field, and you've already done that. I wonder if you can remember the field shape between two attracting magnets. I'll sketch it in and see if this rings any bells. I'm most interested in the bit between the two poles of the magnets that are attracting each other. Now I won't bother filling in the rest because that's, you know, from magnetism topic from year 8. It's not that interesting. What's interesting is the shape of the field in this central region here. Now here you'll see that the field lines are straight and they're equally spaced. When you have straight, equally spaced field lines, this means that the field is uniform. That means it's the same strength, because everywhere in this central region here, the field lines are the same spacing apart, which means the field strength is the same. The field is the same strength. So this section here, the field closely approximates to being uniform. Out here, it doesn't. Out here it doesn't, because the field lines start getting further and further apart. But in this gap in the middle here, whoops, there we go, the field lines are roughly equally spaced, which means the field is uniform. Quickly then, let's have a think about how we could map out a gravitational field. We could do that with a weight on a bit of string, a bit like the compass. We could use that to mark the direction of the gravitational force acting on the weight, and do exactly the same process as before. Keep moving it, make a series of dots, maybe along the wall or something like that, and we would then have a gravitational field line. If we then took a few paces to the side, we could repeat the process again. I'm sure you can imagine where this is going. We'd end up with lots of straight field lines going vertically downwards. Now what does this look like? Well, equally spaced straight field lines correspond to a uniform field, a field that is the same strength. So the gravitational field in the room where I would be doing this looks very much like this, a uniform field, a field where this field strength is the same. But is this really the case? Is the Earth's gravitational field really uniform? Well, no, is the simple answer. Okay, if we were to zoom out and try and repeat the same process, I think you can probably see where this is going. We would use our weight on a bit of string to show the direction the gravitational field was acting to make some field lines. But then if we took our weight all the way over here, it would now be being pulled in this direction towards the Earth. And we would start getting field lines coming in from all directions. Now this is definitely not a uniform field. These lines definitely aren't all acting in the same direction. They're definitely not all equally spaced. This field is described as radial. You can imagine these lines are radiating out from the centre of the Earth, although the arrows point inwards towards the centre of the Earth. So this is a radial field. Now where is this field stronger or weaker? Well, the field lines are closer together nearer the surface of the Earth. So around here, near the surface of the Earth, the field lines are close together. The further you get from the Earth, the further apart the field lines get. So the field is strongest near the surface of the Earth and weaker further away. So that is mapping field lines done, and we've also covered a couple of field shapes, so uniform fields and radial fields. The next video we will look at that in a bit more detail.